Okay, in this video, I'm going to kind of walk through the complex number class that's at the end of Chapter 1 and recommend that you watch this content if you'd like to see a model solution to that problem, and I think it would probably be a benefit to everyone in the class. So let's go through it. Now, at the end of Chapter 1, you have this, this problem, and Drake gives us this UML diagram that I've kind of replicated here. Isn't that pretty? In comments, you see I have a file here called ComplexNumber.java. This is where we're going to build it. And here is the UML diagram. Now, just a little bit about these. They're kind of self-explanatory, but there might be a few things I should point out because they don't read exactly like Java. They're not supposed to. This is a modeling language that is independent of any particular implementation language. But this is the number, the name of the class, complex number, that's at the top. And the next box down here shows the fields that would exist there. That's using the Java language for those. Attributes or fields. And then down here, these are the methods that will exist in the thing. So this, for example, is the name of a field, and this is the name of another field. And after the colon is the type of the field. So in this case, double precision floating points is what that would map to in Java. Likewise down here, this is a constructor. How do I know? Because it has the same name as the class. So that's a constructor. And I see that the parameters the constructor receives are two doubles. Okay. And you know, if we really wanted to be complete, when we had a diagram like this, we would also have a description of each one of these in some additional document. But here they're supposed to be kind of self-explanatory. Drake just says, just implement the complex number class, and we're supposed to be able to understand what these do. So we'll talk about the constructor in a second. Here's an add method that takes a complex number as an argument, and it returns. So see, for methods, anything after the colon indicates the return type. It returns another complex number. The getAngle method returns a double and doesn't take any parameters. Likewise, getImaginary_part, no parameters, but it returns a double. You can imagine that since imaginary_part is the name of one of our fields, and this says getImaginary_part, that is going to return the value of this field. Okay, getReal_part likewise. But this one's a little different, getMagnitude. I don't see a field called magnitude. So my immediate assumption should be probably I don't have a field. I'm not going to define a different field, but instead magnitude is going to be something I'm going to calculate when this method is called. Now think about this from the perspective of something that's going to maybe call this from outside. Okay, make use of your complex number class once you've implemented it. That thing that uses your complex number class doesn't have to know anything about how you're implementing it. It doesn't have to know how you have stored the real and imaginary part. Maybe you're using an array of two doubles. Maybe you've got two individual fields like we have. It doesn't have to know whether the magnitude is stored or calculated. It doesn't have to know whether the angle is being stored or calculated or what. It doesn't have to know anything about it. But we know because we're about to implement the complex number class. And what we know is we just have two fields that are indicated here. So when you see a specification like this, generally, if you're coding to a specification like this, you want to limit your fields to the fields that are indicated here. And you want to limit your methods to the methods that are indicated here. Okay? So anyway, there's more in UML. We could be adding some access modifiers and that kind of stuff, but this is a really good kind of first cut at it just to give us an idea of what's supposed to be there. And we're going to call all of these methods, we're going to make all of those public, okay, so that anyone from the outside can do that. We're going to make this data up here, though. We're going to make that private, so kind of just good encapsulation practice as we learned in Chapter 1, okay? So that will do for now. Let's implement this thing. So first, of course, we'll make the class definition. At the time, we're calling this complex number. Okay, and then that's the end of it. And I always do this. This is really just a habit of mine, which is probably an annoying habit. You don't have to replicate that, but I do something like that. Obviously, if you've got a really short class, you know what that closing brace goes with. But if this thing were to span several pages, it's kind of nice to know what brace goes with what. and it saved me errors before, and just helps me be comfortable that I know what each closing brace is really associated with. I'll do it with methods too if they get beyond just a few lines, but I'll try to break my habit and not do it today in the interest of keeping this a little bit shorter. So let's get started. The first thing we need in this class is to define our fields. So let's do that first, okay? And as I said before, we're going to make those private, okay? So we'll make private double imaginary part, okay, like so, and then I'm just going to duplicate that line and make another one called real part, okay? And guess what? It's just that simple. We're done defining fields. I don't want any more fields in this class if I can help it, because the spec that I have here doesn't show any other ones, and so I really don't want to implement any others. If I should find out that the spec is wrong, I should go and change the spec. Of course, I can't really do that with a textbook, so I'm kind of stuck with what's there. I'm going to try to keep it to exactly what's there and not add any more. So that's kind of a first thing, and I've noticed in some of the programs you want to add something for magnitude because there's a get magnitude method. Don't do that. Just calculate it. Don't let whoever might call that method know whether there is one or isn't one. They don't need to know that. You know that. You know that you're going to calculate it at the time that someone calls it. Now, just for a moment, we need to understand the application area. What is a complex number? And I presume that all of you have had some experience with complex numbers. You know that a complex number has a real part and an imaginary part. Lo and behold, there are fields that are called that. And the imaginary part is a part that is multiplied times the imaginary number I. And what is I? Well, I is this quantity right here, which does not exist in real numbers. That's why it's called an imaginary number. And it satisfies this equation right here, that I squared equals -1. Now you know that nothing squared equals -1 as long as the things that we're talking about are real numbers. Well, it's not a real number, it's an imaginary number. Okay, so this is different. You say, okay, if it's imaginary, why do we care about it? This is used all over the place in math and physics, in electricity, for instance, looking at for example, alternating current electricity and the power that's being transmitted. So imaginary numbers are extremely useful and help to model the real world, even though they don't correspond to something that you can count in any ordinary way. Okay, so it is important in many fields, so I won't defend it any more than that. Nonetheless, we're going to implement a complex number class. So what do you need to know about them? Well, a complex number is comprised, again, of a real part and an imaginary part. The real part corresponds to A in this equation, and the imaginary part corresponds to the imaginary unit, which is I, times a constant B. So you've got a real constant and you've got an imaginary constant. Those are the doubles, by the way, that we're going to be storing in these fields. And you can think of then one of these numbers, since it has two coordinates, it's got a real coordinate and an imaginary coordinate. Think about on a number line, think of that being a one-dimensional coordinate system where a number can fall to the left or right if it's less than or greater than something else. Okay, since we have two coordinates, we really have a two-dimensional kind of number line, as it were. Okay, so here you see we have the real component indicated by RE here, and then here's imaginary, this axis right here. This is the imaginary axis, and you can imagine that point then existing at some point in space right here. Okay, in a two-space where A and B are the coordinates. Okay. Why is that helpful? Because when we go to add them, we'll see that that's just like adding vectors together. You just take one arrow like this that goes to the first point, and you take another arrow that would be the second, and you basically put its starting point at the end point of the other to add these things, and that'll help us when we get to addition. I'm not going to spend a lot of time on complex numbers and the theory behind it, but I encourage you to take a look. And this article on Wikipedia, I know everyone in academia says don't look at Wikipedia. I think Wikipedia is great. Okay, so if you don't, that's fine. But that talks about some of the applications, etc. Let's just go down a little bit. I'll point out one other thing. Since you do have two coordinates here, you can imagine that the angle of this line varies based on the size of the real component versus the size of the imaginary component. If the imaginary component gets larger, then this line kind of stretches up closer to vertical, right? If the imaginary component is smaller compared to the real, then this gets flatter and flatter. So that's one thing to note, is that there's an angle here. And you notice the angle is indicated by phi. And here we have kind of a reflected line. We've got plus and minus the imaginary here. But this angle right here may be interesting. And I'll just point this out that if you want to know what that angle is, it'd be really easy to calculate if you know kind of the real component, which is this x component marked as x here, and the imaginary component, which is marked as y right here. Because all you need to realize is that the tangent of that angle right there is equal to, what is it, the opposite, which is this, right, over the adjacent, which is that. In other words, y divided by x is equal to the tangent of phi. And so the arctangent of y divided by x would be the angle phi. Okay, so when we go to calculate the angle, that's what we're talking about, is that angle. The angle will then, of course, get smaller as the proportion of real to imaginary is larger, and the angle will get bigger as imaginary dominates over real. Okay, so that's what we mean when we calculate the angle here in a little bit. Okay, so I've spent something like 10 or 11 minutes kind of talking about the application. Let's do this thing. Okay, so the first thing we need, let's just do the methods just as we see them from top to bottom. Okay, the first one is the constructor. The constructor is going to receive two doubles. What do you think those are for? Well, one of them presumably is going to be the real part, and the other is going to be the imaginary part. Now, I don't know what order you want to put them in, but we'll name them in such a way that it makes sense. But I'd like to put the real part first, because that's usually the way that, that complex numbers are specified, even though kind of in this UML diagram we had the imaginary part first and the real part second in our implementation. That didn't really matter to me. What I notice is every time we see an imaginary number, it's a plus b times I. So the real part is first, the imaginary part is second. So let's do it that way. What we do there is just public. There's no return type for a constructor that's explicit, because the implicit type is it's going to be a complex number object in this case. So we just say public complex number. Constructors always have the same name as the class, and we know we're going to have two doubles. And the first one, then let's call that real part. Okay, and the second one is going to be the imaginary part. Okay. Now then, what I want to do, this is really simple. I'm creating a new complex number. Okay. And I'm going to receive as parameters real part and imaginary part. Those happen to be the same names as these variables here. Is that a problem? Not really. It just means I need to disambiguate. Because if I were to say something like this, real part equals real part, that would actually work in Java, but what am I actually doing? I'm actually not doing anything, because it will assume that I mean the thing that's in the immediate context, that is this parameter that's been passed in here, instead of this over here. So I will simply set this variable to refer to itself. So that doesn't really do much. But if I do this, now that I have referred to the named field that is part of the object that's being created. Okay, so that's referring to the field. So we'll do that just generally. What I'm going to do here is just do some quick copy and paste to make this a little simpler. How's that? Okay, that's all we need to do with a complex number. And oops, sorry, undo that, and I'm just trying to save it. Okay, so there we go. That's all we need to do to create a complex number. Let's do the next one. Okay, how about add? We're going to use the public access modifier again. And what I want to look at is what kind of thing does it return? It returns a complex number, right? So public complex number, that's what I'm wanting to return, okay? And this is add, and it receives as a parameter a complex number. And what do you think? And of course, we're going to have to give a name to that in a second. I could give it a name like, you know, why did I put the, I don't know, just something random, right? I could give it a number like that, but it doesn't really mean anything, does it? What are we trying to do? What we would like to do is, remember, this is going to be called using a complex number object. So I have a complex number object, and I'm going to call its add method, and I'm going to send another complex number. What do you think I should return? Probably either one of two things. Either I should add the other complex number to this complex number and then return this complex number, or I should create a new complex number, add those two together, and set the new complex number, equal to whatever they add to, and then return that new complex number. Now, this is a decision you have to make because Drake didn't tell you which way to go on this. And it might be the kind of thing that you'd want to document with a comment about what you decide to do. But in any case, I know what I'm passing in. I'm going to call it the add end. Okay? Why add end? Because that means it's something that's being added. That way it at least makes some sense. So let's talk about two different ways then to do this. One of them is this. I could say this dot, here, let's just do it like this. This dot real part is equal to itself plus, that's what that operator means, right? Plus add end dot real part. And let's just duplicate that, but I'm going to use imaginary part. Okay. And remember, I have to return a complex number. So in this case, I will return this. That is one way to interpret the instructions. And again, looking at his, I didn't see that he disambiguated this. I think there's some ambiguity in his instructions. And I would accept either this or what I'm about to show you as a solution. So there's one possibility, is that I actually modify the object that I'm asking to add to the first. The other possibility, and I think this one's more likely, so what I'm going to do is I'm going to just go ahead and duplicate this thing. Okay. So here's another instance of this. Now, this wouldn't compile because I have two methods that have the exact same signature. Well, what I'll do is my first one here, I'm just going to go ahead and comment that one out, okay, as being not the one that I think is intended. Here's what I'm going to do instead. What I'm going to do is I'm going to say complex number result. We'll call it the result, okay? Or how about sum? That would actually be better because result is kind of generic, but sum, if you're adding two things, then what you get is a sum, right? So I'm going to call it sum. Complex number sum equals new complex number, and remember I need to pass in two parameters, two doubles, right? So what are we going to pass? Well, first we want the real part, right? And I'm just going to give myself a little space here to do this. How about this? This dot real part plus add end dot real part. Okay. That's the first double. What's the second double going to be? It's going to be the same thing, except of course it's the imaginary part. So let me just grab these. Bear with me a second. Oops. And let me just get rid of those lines. And then I will return sum. Okay. So what's going on here? Let me clean it up a little bit. Okay, so what have we done? I made a new complex number, okay, a new object. Sum is its label, okay, and I sent it two doubles. The first one is this dot real part plus add in dot real part, so that's the sum of the real parts, and then the second is the sum of the imaginary parts, which is the way that you add complex numbers. So that creates a new complex number, and then I return the sum. Now, do you see how these two are different? Okay, this is not doing the same thing as the one that we commented out here. Okay, this one modifies the number that add was called on. Okay, and then returns it. This one doesn't modify either of the two original numbers, right? It creates a new one, and then it sends that new one back as the result. Two different ways to solve this problem. Again, I don't think Drake specified, and so you're free to do either one that you do. But when you see an ambiguity like that, you should make a comment of some type indicating why you made the choice that you did. That way, when I come and I grade your stuff, if you made a different choice than I did, I understand what you're trying to do. Okay. Let's quickly go through the rest of them. Next one is get angle. I told you about the arctangent, right? And I think if we go into Java, I'll just do this. Java math arctan. Let's just look at that real quick and look at the documentation. And here it is. It's in class math, and let's just go down here to the methods. Okay, look at this. There's absolute value, a cosine. Let's see what the here it is. There's the arctangent. The arctangent is actually atan. That's the method. Okay, it's a static method in math. So this is really pretty easy. Let's just write it public. Oops, what are we doing? It's called getAngle, and it returns a double. Okay, so public double get angle. Okay, doesn't receive any parameters. We know it's going to return a double. That's indicated right here, right? And so how are we going to calculate that? Remember, it's the difference between the imaginary part and the real part. The imaginary, it's going to be the arctangent. So why don't we just say return, and it'll be math.atan. That's the way you make use of that method from the math class. Okay, over here, see that? And what does it receive? It needs a double a. Okay, so what are we looking for? This is the ratio of the imaginary part to the real part is what goes in here. So how do we get a ratio of the imaginary part to the real time? Well, we'll say this dot imaginary part, right, divided by this dot real part. Okay, here you go. So we take the arctangent of the opposite divided by the adjacent sides. Okay, just that simple. And that's going to give us, what's the range? Returns the arctangent. The returned angle is in the range minus pi over 2 through pi over 2. See, this is not in degrees, then this is in radians. Okay, you probably learned about that in geometry for some time. There's get angle. That's easy. Now see, I didn't have to have an angle field in order to have a get angle. I can calculate it as I go. We're going to do a similar thing when we do some of these others. But let's do this one first. Get imaginary part. And so what does that look like? Oops. Public get, here I had it right there, didn't I? Get imaginary part. And what does it return? We need to put that up here. It returns a double. Okay. And what are you going to do? Return imaginary part. That's simple, right? Now someone will say, okay, why didn't you use this? Okay. See, I did use it up here. Did I really need that? Nah. I didn't need it. Why? Because there's nothing else called imaginary part within this context, so it'll get the field that's up here. Okay. So this was unnecessary. Same thing here. It's unnecessary, but I can go ahead and do it just to be clear. There's nothing wrong with doing that. But you can do it either way that you like. And what I'll do now is duplicate this thing, and we'll do the same thing for the real part. And this is just going to be return the real part. That's going to do it. Okay. Now then, the last thing that we will do is in this class is, and I kind of got them out of order, but that's okay. Get magnitude is the last one. Now, what is the magnitude? If I go back to a complex number, that's the length of this. And you know from the Pythagorean theorem, right, that there's an easy way to calculate that. So let's just do it. We're going to get the public double get magnitude. Okay, and what are we going to do? Let's return, and in this case we need a square root, don't we? You remember how to calculate the length of something like this from the two sides. It's just the length of the hypotenuse of a triangle, right? You know that it's equal to the square root of the sum of the squares of the two sides in this case, okay, for a right triangle. So let's go in here, and what we're looking for here is a square root function. I'll bet it would start with an S, so let me just go down a little bit further. And you'll start to learn what's available in some of these things. But look, there it is. Square root of a double. It returns the correctly rounded positive square root of a double value. Sounds good. I'm glad to know it's correctly rounded. I'm not sure what incorrectly rounded means, but in any case, glad to know it's correctly rounded. But it does return, of course, a double, which is what we want. So let's do that. Let's use math.sqrt. So let's return the math.sqrt of what goes in here. It's going to be the square. Yeah, you can use, there's probably a square, there's at least a power function in here. I don't think there's a square, is there? No, but there's a power, okay, L and Q, element OP, QRS, I always have to do, yeah, no, here it is, power. So this returns the value of the first argument raised to the power of the second argument. So you could certainly send double A and double B, where double B is equal to 2, and double A is whatever value you want to square, and you can use PAL to square them. But for squaring things, you know, it's really easy to just multiply the thing times itself. Okay, so what can we do? We can say this dot real part. That will not work being capitalized like that. See that? Okay, so this dot real part. Okay, times itself. Okay, plus, and you know what the next part is. This dot imaginary part, here I'll just do it this way, plus this dot imaginary part times, there's this dot imaginary part, okay? So that's the square of the real part plus the square of the imaginary part, and we take the square root of that, and that's what we return to get magnitude, okay? Now, I will say to you, we've implemented all of the things that are indicated here in the specification, okay? So what else do I have to do in this complex number class? Really, there's nothing else I need to do in order to have implemented what Drake said. But it probably would be a good idea, don't you think, to go ahead and test the class, okay? And I'm just going to sketch that, and then I'm going to let you do it. Now, you could obviously keep this class separate and go ahead and make a main class if you wanted to, like main.java or tester.java or some other file like that, and let that make use of this class. That would be just fine. But another way you could do it, just for something kind of quick, is to go ahead and put your own main in here. And I like it when you write a class like this, at least at this point, I'd like to see you have a main method in the class, or else a separate main.java file or something like that that works out the class, that tests it. And I'll show you more of that when we do the vector and matrix example here before long. But in this case, let me just kind of sketch it. I'm not going to do the whole thing. And you notice, by the way, I haven't compiled this yet. I haven't checked to see if there are any errors. There may well be some errors in this thing. I haven't even tried it yet. I'm going to leave that for you. But you do have an implementation here that works. In fact, I think I probably will test it out a little bit, and then I will upload the code for you. So if you see the code that I upload is a little different, you'll realize that I found an error. Or maybe you saw an error as I went through. But anyway, if I were going to do this, I do this, right? Public. The main method is always static because you don't need a complex number in order to call the main method. Okay, the main method is the entry point of the program, and there aren't any complex numbers yet defined at the time you started. Public static void main. It always has a signature that looks like this. Okay, we have an array of strings, which are the arguments, and you can call that anything you like. I usually call it args. Okay, and that's the main method. Okay, so now how would we test this thing? Well, we'd create some complex numbers. You could do something like complex number A, B, C, and D. How's that? Okay, I'll just define some, and now I want to initialize them. Okay, A equals a new complex number with how about the real part is minus 1.5 and the imaginary part is 0.65. I'm just making it up. Okay, it really doesn't matter. Okay, so there's A is a new complex number. I could say that B is a new complex number, and we'll make it a little bit different. Let's let it be 1.2 and 1.65. I don't know. 1.35 there. It doesn't look like I tried to make it the same. And maybe we'll say that D equals A dot add B. Okay, you know how B works, right? I could do something like double angle of A equals A dot get, what was it? Get angle. Okay. Let's just do one more thing. How about the magnitude of one of these? Let's double mag of B equals, and I probably should spell that right. All right, so double, oops, Okay. Okay, mag of b equals b dot get magnitude. And now what would I do? Maybe I print some of these things out. Okay, something like that. And that could be helpful. Okay, so like system dot out dot print line, magnitude of b is, and then I just add mag of b. Okay, something like that. Now that's one way that you could do this. There's one more thing you could do that would be really helpful though. Wouldn't it be nice if once you've created a complex number, you've done some things like that, if you could just really easily print out all of the essential things about a particular complex number, so you can kind of test all the methods at once and see what that might look like. Why don't we override the toString method that exists for every object, okay? So that we return a string that gives you kind of all the stats about this particular imaginary number. What would we want to do? We might say something like, this is a complex number, right? So what we might say is something like, let's say string result equals complex, say, and we could say, how about let's add the get. Now this is not static, this is being called from a particular object, so I'll have like a dot toString. Okay, so I have an object that's this object, so it's implied whenever I call a method. So I'll say get real part, like that. Okay, and then plus, and how about the a space and then the plus sign. Okay, and now let's concatenate also the get imaginary part. Just getting a little long? Yeah, it is. Let's break it up. Okay. Okay, so now we add the imaginary part to it. Okay, and then maybe we want the something that says times I, right? So we'll add I after that. Okay, and how about we'll just put a semicolon there, and then let's add something else. Okay, how about plus? You want to say what the magnitude and the angle are? Magnitude equals. I'll put the equal sign a little closer associated, and that's caps. I don't like it. Okay, magnitude. That's too much. How about just mag? Mag equals, and then we'll plus get magnitude, and then that. That's a method call, right? And then what do we want to concatenate after that? How about a comma and a space, and then we'll say angle equals. Okay, and then we'll add the get angle for this. And what else do we need? How about just a period? Okay, and now we'll just say, now that we've made a string, we'll just say return result. I could have just said return and then all this whole string thing. So what have we done? We've concatenated a string together from various parts. We have the word complex, colon, and a space, and then we have the real part, which is going to be printed out next. It's going to be added to the string, and then plus, and then the imaginary part, and then plus, and then the letter I. So what is it? That's A plus BI, right? Whatever A and B are, it's going to actually print it out. Then next we said mag equals, and we get the magnitude. Then we have a comma, space, and then angle equals, and then we get the angle, and then we stick a period at the end. Okay, so that's our toString method. So you could do something like this. Now that we've done this, is get rid of this silly stuff. Okay, and let's just do something like system.out.println, and we'll say a dot toString. Okay. As a matter of fact, if you just put a in there, that would actually be sufficient, because it will call the toString method of a. But you can be explicit like this. What we could do is say a like that, and then concatenate a to string. How about this? We'll do the same thing for B, and we'll do the same thing for C. Now look at that. We're going to get a nice output now. And again, I haven't even run this thing yet, but I think you'll find that if you run it, now there might be some errors in it. I'll check it out before I upload it, but we're at 35 minutes. I'm going to stop now. Okay, but that is an implementation of this complex number class. Just a first cut at it. And you see it's not that big, but you know, it takes a little while. It took half an hour to punch that out. But this is going to be the kind of thing that you want to do when you look at something like this. You want to convert that into Java code. This is what you're looking for. Okay, that's enough. I'm going to cut it off right now because it's getting too long. And in the next video, I'm going to do something with the vector class as I promised in class.